All right, so very quickly, let's talk about how you make alkynes. So just back up a little bit from where we are. How do you make alkenes, right? You take an alkyl halide and you do an elimination. The way you make alkynes is you take a dihalide and you do 2 eliminations. So we call it double elimination, right? Like basketball or whatever the tournaments are. So really all you need is a strong base to do this. Now, the trick with forming alkynes is you need a very strong base because you're doing an elimination reaction. If you think about the mechanism real quick, how you might imagine the mechanism would look. You have, I'm going to write it like this. It's easier to write these like this. Oh, look, it's working because I can't write. So here's my dihalide. You know, all the rules of anti-periplanar and all that kind of stuff still apply. Okay? But a base will come in, grab this off. This bond breaks. This bond goes to the chlorine. The first step in the formation of an alkyne is actually an alkene. Okay, so in the second step, again, the base has to come in, attacks the hydrogen, pulls that off like that, and that forms the alkyne. Oops, ran out of space. And then you get something like that, okay? Right, so this, right, pi bond, high electron density, you need a really strong base to push the electron density into here. So as a result, using something like sodium hydroxide or ethoxide might work with this kind of arrangement, right, but you need a much stronger base in order to pull this one off. And so this is why we normally use, and this is what I talked about last time, sodium amide, or something like sodium amide. Yeah, NaNH2, which really this part is what we're interested in, is NH2 minus. 2 pairs of electrons. Very strong base. pKa of ammonia is like 35. So its conjugate base is very, very strong, okay? Because as an acid, we usually think of ammonia as a base, right? But ammonia as an acid is very, very weak, and as a result, its conjugate base is strong. Okay? So that's the kind of base that you need to complete this reaction. Okay, so E2 reaction twice forms the alkyne. You can also do the same reaction using what are called vicinal halides. So this was geminal halides that we talked about first. Vicinal halides do the same thing, and you might think that you would get this instead. Oops. But we haven't really talked about this. You might think you might get something like this instead. Okay. So what's to keep the bond from that? You can form one here, but what's to keep the other bond from pulling a hydrogen off next to it, right? So you have to realize these R groups on either side have hydrogens on them. So what's to keep it from making what's known as accumulated diene? And although we haven't discussed it, accumulated dienes are very, very unstable. Okay, so alkynes actually turn out to be, it's the same number of pi bonds, but alkynes actually turn out to be a little bit more stable. So even when you have vicinal halides like this, you still get an alkyne out at the end. Okay. Any questions?
The opposite of like being conjugated, where they're separated by.
Yeah, so yeah, these are not conjugated, right? They're called cumulated because if you think about the p orbitals on this pi bond and the p orbitals on this pi bond, they're 90 degrees to each other. So it doesn't allow for delocalization. So basically all you did is take all the electrons in the pi bond and shoved them onto one carbon. So that's what makes it unstable. Yeah, on the central carbon. And so it turns out when you do like combustion analysis, basically alkyne is more stable than the accumulated diene. Same number of pi bonds, it's just more stable. So that's why you end up getting alkynes even with vicinal halides. Okay, so one of the little side notes on the preparations of alkynes is that when you use sodium amide, we usually do it in ammonia. What is ammonia? What state is ammonia normally in? It's usually a gas, right? So again, this kind of reactions run at very low temperature. I talked about this before. I usually run at like -78.
Liquid ammonia?
Yeah. And the way they get those temperatures is they take dry ice, put it in acetone, and then they put a Dewar reaction vessel inside there, and then they condense because the ammonia comes as a gas, so you have to condense the ammonia into the Dewar. Kind of a weird thought, right? Okay, so anyways, problem is there's usually an excess of amide here, and we talked about the pKa's before. Acetylene, all right, is acidic enough, pKa is like 25, that the excess amide will tear that hydrogen off and leave you with, they call it an alkynide ion. A lot of people will just call these acetylide ions, triple bonded carbons with a negative charge, okay? So after they do this part, you really don't have your acetylene yet or your alkyne yet. So typically what they'll do is they'll react it with something that is that's more acidic than acetylene. And basically everything that we deal with is more acidic than acetylene. So water, alcohol, anything like that can be used. Weak acids are used. Okay? So when you see these things written out, just very quickly, when you see these things written out, they're usually written out as, here's the dihalide, right? My internet is slowing way down. Hang on. Need to pause this thing. Right. So what you normally see is, that's really slow, is that they have this excess sodium amide. That's to ensure that you get a high yield of the alkyne. And then they add this afterwards. And this is simply just to protonate the alkyne that's been formed at the end. Okay, so we start talking about, well, I wanted to start talking on the slide. I can't actually remember if I did start talking on the slide. Reductions of alkynes, okay. When we did reductions of alkenes, we would use like H2. Hydrogen, metal catalyst, and you get an hydrocarbon out, okay, an alkane out. So hydrogen, metal catalyst. I'm not sure what's going on. I'm pointing in a place, but it's just going crazy on me. There we go. And a metal catalyst. And then as a result, you end up getting the alkane. Turns out if you do the same thing to an alkyne, you get the same product out. Okay? It goes through this intermediate, right, the alkene. But turns out alkenes are more reactive than alkynes. And as a result, once you form the alkene, this is like the rate determining step is to form the alkene, then this is the fast step. This happens before you can stop it. Okay? So as a result, you end up with an alkane. It starts off as a cis because the hydrogenation takes place on a surface, right? And the hydrogens both get added from the same side. So the triple bond, when it's broken, the second pi bond is broken, both the alkyl groups go up in the same direction away from the surface. Okay? Okay. Huh? Should have been the other way, huh? Would look better. right? Because you think of the surface as being down here, right? So now the surface, for some reason, is at the top, and the hydrogen's got at it. Anyways, I get what you're saying. So in order to keep that from happening, what they use is there's two types of reagents that get used for this. One is known as a poisoned catalyst, and the common name that we give it, one of these catalysts, is known as Lindlar's catalyst, or another one is this P2 catalyst. And basically what those are metal catalysts that have been deactivated. Okay, deactivated means they got them dirty enough. I mean, this is basically what you do. You foul up the surface enough so that the rate of the second hydrogenation is slow. Okay.
So you make the reduction of the alkene the rate determining step.
Yeah, so you're basically making the alkene formation the rate determining step. And now the alkyne reaction takes place. You get 1 mole equivalent of hydrogen attached here, and that to the triple bond, and you end up with a cis double bond that comes out as the product. Okay? So like I said, Lindlar's catalyst, all they do is they've added quinoline, palladium on barium sulfate, and they use methanol for this, or this nickel boron complex, this P2 catalyst, is also used for these things. So in essence, what I was talking about before, right? They take the first step and they leave it unaffected, and that reaction is catalyzed. And what they do by fouling the surface is slow down the second step or leave the second step unaffected.
Wait, the blue is catalyzed?
No, that's the step that's catalyzed, and the activation energy diagram for the catalyzed reactions in red.
Oh.
Yeah. Okay. There's another kind of reaction which is known as a dissolving metal reduction reaction, and the reason that people will use this is because it allows you to make a trans double bond. Okay, so it behaves like the poisoned catalyst in that it will reduce a triple bond to a double bond. But what's different about it is it allows for the double bond to be in the trans position. Okay. Again, liquid ammonia, done at very low temperatures. All right. So let me show you what's going on. Why can't water be used as a solvent for this? What's that? It's going to freeze, and it'll react with the sodium. Yeah. But yeah, primarily it's going to freeze. Okay, so here's the mechanism. And this is the first time we've seen a one-headed electron arrow. So if you look here, this electron arrow, all right, has one barb on it. So the sodium metal, what's sodium cation's charge? +1, right? So the sodium metal, which is sodium 0, gives up one electron, becomes sodium +1, and then you form this anion, okay? This is known as a radical anion. It has a single electron, an odd electron here, and a lone pair of electrons here. The lone pair you get because the pi bond, when it breaks, one electron goes to this side to make a pair of electrons, and the other electron... I just realized I did something stupid earlier. The other electron goes to this other side because you can't have 3 electrons here, and so the electron's got to go somewhere, so it sits onto this carbon. Okay. Now, yeah, they call these fish hooks. Why do they call them fish hooks? Because they look like fish hooks. Okay. All right, and I guess I should ask this question: why does sodium metal so readily give up an electron? It gives up one because it only has one, and it gives it up because it's more stable as the cation. Yeah, it's more stable. All right. Okay, so that's the first step in the mechanism, and you'll notice what happens. You have these 2 electron clouds, right? And if the pi bond breaks and the R groups are in the cis configuration, you have these two electrons clouds that repel each other. Okay. Now, this is still a pi bond, right? Still can't rotate. But the electrons can actually oscillate through, like flip through the orbital. Because remember, there's an orbital part over here and an orbital part over here. They can actually get away from each other, not by rotating necessarily, but by the electron cloud moving through to get away from the other electron cloud, so the other electron repulsion. Okay.
Is there positive charge on that alkyne where that sodium attacks? Like what drives that sodium attacking that specific?
Yeah, so what is the hybridization of the carbon? And what does that mean about that carbon? It's more S-like. So what does it mean about electrons? Closer to nucleus. So it'll pull those electrons in simply because it's sp hybridized, rather than going to some other point on the structure. Okay. All right. So once you have this anion, okay, and it's in the trans configuration, this is the way that it forms the best, okay, with the electron groups away from each other. Then it can pick up a hydrogen from ammonia, and you have to remember this is an alkene, so the pKa's got to be around 45 or something like that. It's going to be a stronger base than ammonia is, right, than amide is, and so it'll pull that hydrogen off. And then it'll pick up a second electron from a second equivalent or second mole of sodium. Okay. So you get the first electron and the radical anion. You pick up the hydrogen, and then you get the second electron, and you get an anion again. And then this anion can now pick up a second hydrogen, and this is how you end up with the alkene. Okay? And the configuration for the alkene is in the trans configuration. Go ahead.
So this is a dissolving metal reactor reduction. So you take a solid metal and you add it to liquid ammonium.
Yeah.
The reactor.
Yeah, I've never done this reaction, but apparently it dissolves as the reaction goes on, or it dissolves into the solution.
Right, because the sodium is losing its, like, it's going from solid with one electron to
Sodium plus, and it's in a
aqueous.
polar solvent. It's not aqueous.
Oh, it's in a polar.
It's in a polar solvent.
Liquid's a little bit crystalline.
Yeah. No water.
Sodium
Awesome.
Yeah. All right. So I hate drawing the bottom one. What's the top one going to? So this is sodium, right? And ammonia, liquid ammonia. Product is going to be what configuration? Trans. This is what I suggest you do when you do these. Write the numbers on here. 1, 2, 3, 4, 5, and 6. And then what you want to do is you want to draw a six carbon parent chain. And double check that you have the right number of carbons. So 1, 2, 3, 4, 5, 6. And when you draw these out, right, it's already in the trans configuration when you draw it like this. So all you have to do is remember that the double bond goes between 3 and 4. So that's that product, okay? If I had done Lindlar's catalyst, then I would have done 1, 2, 3, and then I have to remember the configuration is cis. So these ones are actually harder to draw. 4, 5, and 6, like that, and then you draw the double bond in like that. Okay? But again, number the parent chain, because a lot of times when you have triple bonds, you lose track of the carbons because it's linear through that point. So number those carbons before you actually draw the product. And then draw your product based on where the double bond should be and what its configuration should be. Okay, so again, we're going to do that same one with this. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now you have to draw an 11-membered ring with a trans double bond in it.
Why does the one go on the carbon and not on the alkyne?
Oh, doesn't, for the purposes of drawing the product, it doesn't matter where you number it. If you're naming it, you would have started where the 2 is and counted across. And it would have been cycloundecyne, I guess, but yeah. So now I have to draw an 11-membered ring, and this is just always horrible. So 1, 2, 3, 4, 5, 6, 7. And what's the configuration have to be? 8. I'm going to make this up. 9, 10, 11. Yeah, that's pretty ugly. Sorry.
It's not supposed to be like a circle, you want it to be like a snowman.
Yeah, so like large rings, the sides a lot of times tend to fold in. Rather than being completely circular, they tend to have folded insides. Yeah, so have fun drawing those.
No.
I promise you I will not have you draw a cyclic alkene, an undecking, or yeah, anything like that, because I hate looking at them for one thing. And okay, so so you need to be familiar with these reagents and how these transformations are done. So if you want to make a cis double bond, then you would use Lindlar's catalyst. If you want to make a trans double bond, then you use the dissolving metal reduction reaction. If you want to go to an alkane from either one of these, then you can do hydrogenation from either one of them, or you could hydrogenate the alkyne and get to the product directly. Okay. Now, if your goal was to make a cis or a trans, then of course you wouldn't do this second step of hydrogenation. And if your goal was to make an alkane, you wouldn't do Lindlar's catalyst in sodium dissolving metal reaction, sodium and liquid ammonia. All right, so hydrohalogenation of alkynes, it's similar to hydrohalogenation alkenes, follows Markovnikov's rule. The hydrogen goes to the carbon with the most hydrogens, but then on an alkyne, right, one side generally doesn't have a hydrogen. And one side, the only way you can apply that rule is when it's a terminal alkyne. So when you do this reaction, right, the first one adds just like you'd expect for Markovnikov's rule, right? The second one does as well. Okay? So what ends up happening is you'll end up with a product that looks like this. Oops. Working? Oh, it's kind of not working, my slides. I'm telling them to change, but they're not really doing what I want to. Okay, anyways, you're going to end up with this. Ooh, it looks very unhappy. Actually, it looks dead. I killed my molecule. All right. So in the mechanism, for hydrogenation of alkenes, right, you form a carbocation and then the nucleophile attacks, right? And you form the product, and as they say here, it's an equilibrium. But if you do it with an alkyne, okay, turns out when, and you look at the rate law for this, okay, the rate law for this is bimolecular. That is, it's the concentration of the alkene and the alkyl halide. It requires both. When you do the reaction with an alkyne, turns out the mechanism, the rate law, is termolecular. So it's one of the, we talk about generally, there's not a lot of rate laws where three molecules have to collide at the same time. This happens to be one of them. And it depends on the concentration of the hydrogen halide squared. Okay, so what that tells us, or what it implies to us, is that in the rate determining step, there's two HXs involved in the rate determining step. So how do you imagine that happens, right? So this is what people have imagined happening. They imagine that when the alkyl halide is attacked by the pi bond, right, you're going to form a positive charge on an alkene. So let me ask you a real quick question. What is bad about or unstable about that kind of structure? What's that? Not very substituted. What's the hybridization of this carbon?
Yeah, that's the wood bond.
It's sp hybridized, right? It only has two groups on it. So as a result, it's a very like electronegative kind of atom. It holds whatever charge it has very close to the nucleus. And because that charge that it has is positive, and what's the charge of the nucleus? Positive, right? That's a very unstable structure. So these vinyl carbocations it was working so good. Are very unstable. And as a result, what they say happens is, and this is what the rate data tells us is happening, is that this bond is formed while this bond is formed. And that way you get a partial positive charge at this point, and not a full charged carbocation like you would expect in like a reaction of an alkene. Okay? Because in the reaction of the alkene, what happens? You break the bond, you form a carbocation, and the nucleophile attacks. Because this kind of carbocation is so unstable, what they say happens, and what the data shows happens, is that this bond must be forming at the same time this bond is breaking. This bond is forming, and that lowers the amount of charge that you see at this vinyl carbon. Okay.
Is this considered concerted as well?
Yeah, so it's a concerted. If they're all involved in the same step of the rate law or the rate determining step, then it's a concerted step.
So you said it was unstable because the positive charge.
Yeah, the positive charge. And if you think about the hybridization of this carbon, it's sp hybridized. So sp hybridization likes negative charge because it can hold that close to its nucleus, and for the same reason hates positive charge. Does not want that close to the nucleus. So that's what makes it unstable. Peroxides do the same thing. So you can get anti-Markovnikov behavior with peroxides, just like you can with alkenes. But because it's a double bond, you get a mixture of E and Z isomers, because it could be cis or trans, if you want to think of it like that. Okay. Oh yeah, which one's E? Yeah, this one, this group, and this group are high priority, and this is Z. They're the high priorities are the same side. Okay. I'll show you one other thing about these reactions. Important sort of conceptual thing anyways. Pen color. Take an alkyne. And then you do two equivalents of HX, okay? you get one product in this case. Like that. Okay. What other possible products could you see forming?
One where the X is on one.
Yeah, ones where X's are on other sides. Okay, so this is definitely the minor product. This is your definitely major product. Okay, so why does that happen? It involves the mechanism of the reaction, which you would expect to be similar to so the pi bond breaks and attacks here. So that means this bond has to form at the same time. Okay? That's the mechanism we just showed. And you'll end up with and these will be in a trans configuration. Okay? So now this is just an alkene, and it's an alkene that's going to react to form an alkyl halide, or dihalide. So if you follow that mechanism, take HX, the electrons from the pi bond attack the hydrogen, right? And then the X pops off. And then you can form two different carbocations. That's one of the carbocations. And the other one is that. Which one leads to the major product? The first one. Why do you so what does that tell you about if these are the intermediates for the products, like directly above them, okay? What does it tell you about the intermediate on the left? It's more stable. So then the question, right? Then the next question is, what would make that more stable? It's not the electronegativity. That would make it less stable because it would take more electron density out, right? And we talked about putting. Yeah, but positive charge is not stable. What's that?
It's because of the on the left is a tertiary structure.
Yeah, that's closer to the right thinking. It's not tertiary, but that's closer to the right thinking. What makes carbocations more stable? Hyperconjugation, electron donation, right? So what is it about X?
The size of it and the electrons.
And its electrons, yeah. Its size and its electrons. Okay, so it turns out you have lone pairs of electrons on here. And they can donate like that. And it creates a resonance structure. Now, that's the resonance structure of that molecule, right? Doesn't necessarily say that that's like a stable molecule, but in general, when you can draw a resonance structure, that structure is going to be more stable.
I'm more late, but the keto-enol thing, is that kind of what was happening with the oxygens? Why they were, I know it's like.
Yeah.
But that was
Not
kind of
totally
what I thought.
different. Actually, we cover the keto-enol thing in the next section, so we'll look at it. You can ask your question there. Yeah. Because enols are formed all the time in hydration of alkynes. Okay, so see, enol. So when you do the hydration of an alkyne, remember alkynes are not as reactive because an they don't like the positive charge building up on the vinyl carbons. And so when we do hydration of an alkyne, we use mercury sulfate as a catalyst, and the mercury ion helps to stabilize the pi bond, which allows it to be more reactive. It still follows Markovnikov's rule, where the oxygen gets added essentially to the more substituted side, and the hydrogen gets added to the side with more hydrogens, or the less substituted side.
Also mercury what?
Mercury sulfate
Uses
as a catalyst, yeah. And it stabilizes this guy. Oops.
Sulfates count as a sulfate base.
Not really. We don't use it for that very often, anyways, not that I can think of. So stabilize, so the mercury part of it, this part, I should just circle that, stabilizes pi bond. And that helps to lower the activation energy and allows you to form the carbocation on that secondary carbon. Okay, so you form an enol, which then what we say, the terminology is it tautomerizes. To form the ketone. And the ketone turns out to be a lot more stable than the enol, simply because this bond is more stable than this one is. Okay. It looks kind of like resonance, but because you get an atoms moving, the hydrogens moving, it's a constitutional isomer. They call this a tautomerization. Okay.
Sounds like an automaton.
Yeah. Right. All right. Let's see.
Automaton? So like a little machine.
So this is sort of the mechanism under acidic conditions. This is the mechanism for the tautomerization. Okay. Here's your enol. This bond can break and attack the hydrogen. It's done under acidic conditions. So then you're left with water over here, so that's stable. And you're left with this carbocation, and then you can have resonance between this oxygen and the carbocation that's next to it, just like you do when you do the reactions with the halides. And the halide can stabilize the carbocation, so it makes that reaction a little bit easier. So once the pi bond gets formed, then all you have to do is deprotonate it, and then you're at the ketone. Okay? Generally speaking, ketones are much more stable than enols. The only real exceptions that we see, like commonly, are this particular enol. Yikes. This is an enol. Phenol. And the reason that enol gets formed is because the benzene ring is very stable. So, you know, when we talk about enol formation, normally it's the stability of the C double bond O that is a driving force, but when it's between the double bond and a benzene ring, and the benzene ring being more stable, right, this is the preferred form for this particular enol. Questions? Where have you seen that before? Think lab. Yeah. The one you're turning in soon, next week? Formal, typing it up. Yeah. All right. Hydroboration also works. So you remember this reaction is just from last lecture. Hydroboration also works on alkynes. And it does exactly what you expect it to do. It makes adds the oxygen to the less substituted carbon. Right? The mechanism is the same as the hydroboration reaction for alkenes. Okay? You end up with an enol then, and if it's a terminal alkyne, you end up with an aldehyde. So this is done under basic conditions. So it turns out this enolization, keto-enol tautomerization reaction is also catalyzed under basic conditions. So if you have an enol that looks like this, then the OH is a strong base. It attacks the oxygen, the hydrogen attached to the oxygen, which then interconverts to the keto form, and then this picks up a hydrogen from water, or the solvent in this case, and produces the aldehyde from the reaction. Okay? But so the tautomerization of the enol is catalyzed by both acid and base conditions, but the mechanism is slightly different. Let's back up for a second. So let me ask a question. How would you, like, let's say you forgot this mechanism. How would you remember what the first step is?
OH is bad leaving group.
OH is a bad leaving group, that's one thing. But if you're given acid under acidic conditions, the first step is usually the addition of the proton somewhere. Okay? So try to remember that. Yeah, so the pi bond can be the nucleophile, the hydrogen gets attached. So one of these things that I notice that people like forget, not all the time, but frequently, is when they're looking at the reaction conditions, if it says it's done under acidic conditions, that's usually there for the first step of the reaction. If it's done under basic conditions, it's usually there for the first step of the reaction. And so that's usually like a guide to help you follow through and do the rest of the mechanism, or at least start the mechanism off correctly. Here's the other thing I wanted to point out to you on this mechanism. Under acidic conditions, you can't have any negative charges. What's that? There won't be any negative charges in your mechanism if you have acidic conditions.
The entire like reaction mechanism?
Yeah, and the whole thing.
There's gonna be the negative charge.
Yeah. Why is that, do you think? I mean, it seems like a really big generalization, right?
Because then the hydrogen wouldn't be catalyzed. It would be not conserved.
Well, yeah, and then under acidic conditions, anytime you would form an anion, right, that step will always be faster if you protonate it first. What's that? Okay, so let me show you one other thing. If sodium hydroxide is used as a catalyst for a reaction, like if it's the catalyst, it's usually for the rate determining step, and usually that's a proton transfer, okay, or a nucleophilic attack. It's one of those two things.
And then under basic conditions, where there usually be no positive charge.
There's no positive charges. So those are good general rules to remember when you're drawing mechanism. Oh, I'm doing this with sodium hydroxide or sodium methoxide, and you end up with a positive charge, that means you forgot to deprotonate something at some point, right? So you back up and you figure out, how do I get rid of this positive charge? And if you can't do that, you're going down the wrong path in the mechanism.
And then is that just for hydrogenation?
It's for, just in general terms. Okay, so hydroboration, oxidation, I'm just going to walk you through this mechanism. Real quickly, and talk a little bit about some of the things that are wrong with hydroboration, using borane as the reagent, borane being BH3. First of all, this addition to the alkyne can happen twice because you have two pi bonds. Okay, so when you have two pi bonds, turns out there's two problems with this. The borane could add here, or it turns out it could add in the opposite direction as well. Okay, one of the things that controls the regioselectivity of boron is steric hindrance, and alkynes have very low steric hindrance. Okay, so there's one problem. The other thing that can happen is you can get boron, right, added twice to the same alkyne, and that leads to something that we don't want. We were looking for an aldehyde, right, and then you'll end up with either a double alcohol or something like that. So what they do to get around this problem was when they do the hydroboration reaction with alkynes, they tend to use boron reagents that are already disubstituted. Okay? So what does that mean? It means it can only add once. And it also means it has steric hindrance built into the molecule, so that gives it its regioselectivity, because the alkyne doesn't have that steric hindrance around the structure that an alkene would normally have. Because remember, alkenes would be branched, right, sp3. And so alkynes don't have that. And so we tend to use these oddly sterically hindered boranes. So I can't even say it. It's a diisoamyl, but it's a secondary isoamyl. So it's a di-secondary isoamyl borane. So that's a di-secondary isoamyl borane. Or this BBN, which is this bora bicyclononane. Anything that looks like this with two alkyl attachments to a boron will work for this kind of reaction. And whether it looks like this or it looks like this, the whole purpose of that is to add steric hindrance, one, and two, to prevent the secondary addition of a boron. So each boron can only add once. Okay, so what happens when you do diisoamyl borane? You notice the second step is still the same. You'll end up with, again, if it helps you, number the carbons. 1, 2, 3, 4. So 4 carbons. And because it's a borane, it's a hydration reaction that occurs in the anti-Markovnikov fashion, so the O will end up over here, and you end up with an aldehyde. Like that. Do you guys follow that? Did I skip too many steps in between? So back up. What this reaction does is put an OH group on the less substituted side. This is an enol. So it's going to convert itself to have the more stable C double bond O. So that's what we end up with over here. Okay? So in this reaction, when you're looking at
So the OH is gonna go on the other side of the.
yeah. So your OH, let's draw a little intermediate product here. That's what you end up with, but that after the boron is expelled off, right? So this H from the H2O, this gets pulled off. Well, anyway, sorry, back up for a second. This is the reagent that we get from this combination. So this O, right, gets attached to the boron, and then the R group, the alkene, gets shoved off onto that oxygen. That's what this structure is. Okay? But that's an enol, right? So enols are less stable than their keto forms. So this one will interconvert to the keto form and form the aldehyde since it was a terminal alkene or alkyne. What would you have used to make this? Oops, this guy here. So what's the alkyne that was used to make that, and then what reagents would you use to make it? So a couple possibilities, right? But the alkyne has to be what? Has to be terminal, because you can't fit a triple bond there, right? So if I use diisolamyl borane, where would the OH get attached? To the left side, and what would I end up with? Let's do that, okay? We'll draw it out. So that's going to tautomerize. Where's the C double bond to O going to be? Be going downward on that last carbon, right? So I end up with the aldehyde. Is that the product? No. So I need the O to attach where? I need to have it attached there, right? So that's going to be the first reagent that we just a regular hydration, because that's a Markovnikov addition to an alkyne. So it's the mercury sulfate, and then like H3O plus. You know, strong acid in water. All right. Let's see what else I have. Hang on, let me pause for a second. What kind of addition is the halogenation reaction? Is it anti or syn? It's anti, right? So the halogen groups have to end up on opposite sides. Now, if you have an excess of halogen, you automatically get 4 halogens added, right? 2 to each carbon on either side. If you have one equivalent, so there's 2 pi bonds in here, right? We use this term one equivalent. So if I had 1 mole of alkyne, I had 1 mole of halogen. The major product ends up being a trans dihalide, okay? Because of the anti-addition of the halogens. And then a minor product would be the cis halides when they're on the same side of the molecule. Okay. And like it says down here, how it actually happens that you get this product is they don't really quite understand how that happens. So, yeah, so that's one of those things. Like in organic chemistry, they're pretty good with, yeah, we can use this and make stuff happen. Yeah, we're not exactly sure yet. But here, you got to learn it anyways. So. The solvent is got to be one of my favorite all-time solvents is carbon tetrachloride. It's like the best thing ever for removing road grease from your car, except for it's really bad for the environment and you can't buy it anymore. But besides that, my mom showed that to me. She's like, oh, I had all this road grease on my car. She says, oh, I've got carbon tetrachloride in our garage. I'm like,
Do you have any more?
no, I think we used it all up or it evaporated. But it was this old bottle with, like, came from the, we used to be able to buy it at the pharmacy. She was a pharmacist, yeah. So I was probably 50 years old. And you just put, right, but you put it on the cloth, and like all that really thick road grease you get on the bottom of your car, you just go one time and the whole thing comes off. Pretty good.
Why is it bad for the environment?
Halogenated compounds are generally bad for the environment, and they supposedly cause cancer.
Oh.
Yeah. Supposedly. That's what they say about all organic compounds. Okay, so you can also do ozonolysis. Thing I want you to remember is when you do ozonolysis of alkynes, you get the more oxidized product. I introduced the idea of more oxidized and less oxidized. So if it's an internal, internal, whoa, that was weird.